fundamentally different from each other. And so every risk measure that I'm going to introduce, you will find two formulas for that in the slides. Right? So, and I want to talk about why we need the two formulas. So the first part, we're going to basically discuss one way of doing this, and then I'll show you how to do that with real data. But why do we need these two perspectives, basically? So that's the, don't have a slide for this. I think it's somewhere hidden on multiple slides. So I would generally call the two perspectives a forward-looking and a backward-looking perspective. And I've already used terminology that kind of allude to this. So we have, for example, talked about expected values. Right? Expectation means you look into the future and figure out what possible things could happen. So that's a forward-looking perspective, right? Expectations. So the things that you need, or the information that you need, is you need information about the possible scenarios that could happen and the probabilities. And the concepts of math that you use behind it are from the area of probability theory. So this perspective is generally taken in most financial theories. Right? They're forward-looking. Their risk is something that about things can happen in the future. Right? So the big problem is, how do you know about the probability? Right? So that's something that, well, I just told you in my examples. I just told you the numbers, but how do you figure out a probability in real life? Let's maybe think quickly about it. Let's suppose you want to figure out the probability of a coin flip, but you don't know it, right? So how do you figure this out? Well, you have a coin available to you, but you don't know the probability.
I'm taking the number of, let's say, results.
Okay. Which results? So how would you do that? I just gave you a coin, right? There are no results.
So I have two outcomes, and I can have only one result per try.
Yeah.
So
now you're thinking theoretical, right? I have two outcomes, and looking, staring at the coin, they look kind of similar, so the two sides. So how would, if you can run an experiment, how would the experiment look like? Yeah, flip the coin. You would do that 1,000 times, not only once, right? 1,000 times, and then you would look at how often does heads appear and how often does tails appear. And the frequency of an observation is your estimator for the probability. If you don't know that, that's the way that you try it out. Right? Or if you have a dice, right? Well, the dice has 6 outcomes, but you only figure out the probabilities by rolling the dice very often and see how often does the 1 come up, how often does the 2 come up. And that's the way if you want to identify weighted dice, so people use that in gambling, right, to get an advantage. You would just see if the 6, for example, appears much more often in your sample, then it's a weighted dice, right? So that's the most easy way to figure it out. Right? So the probability of that should correspond to the frequency of the number appearing in your sample, basically. So what you did is you looked at data and learned something about the probabilities, right? And that's the learning about data is our backward-looking perspective. So we look at the historical data, what happened in the past, to learn something about the probabilities, right? Because in finance, it's not so easy to look at it like a coin and know the probabilities. So you need to kind of figure out a different way. The concepts that we're using for that are from statistics. And even though you might study that in the same class here, and most of the time these are two different fields of math, right? So this is about expectations, that's forward-looking, and this is about handling observed data. Right, there's biases in there, right? So econometrics is on the right-hand side, and basically standard math is on the left-hand side. In econometrics, even those two perspectives have different names. So this is sometimes called the population, and this is called the sample. Population means that you know all the parameters, like probabilities and so on. Like for a dice, you know that there's 6 sides with equal probability. You know that the expected value of the dice is 3.5. I think it's evidently it should also be equal to the standard deviation of the dice, right? So you know the properties, that's population. In the sample, you would generate data. You would roll the dice 1,000 times, and you have observations to learn something about the unknown parameters of populations. So the concept here is called population. The German word for that is Grundgesamtheit. And the sample in German would be Stichprobe. Population means basically perfect information about everything. And if you look at theories, in theories usually we do that, right? Like the state price example, right? I told you the numbers, right? But in real life, we need to do this to figure out what those unknown numbers are. So this is basically mainly used in theory, and this year, and this is basically my field of research, you can use that not only to find out about the unknown probabilities, but you can also go and test theories, right? The theory has a prediction, and then you can see, does the prediction hold in the data? And the last thing where you could use the backward-looking perspective is about forecasting. If you want to know how interest rates are 2 years ahead, right? And you would basically look at past data and extrapolate that. Basically, risk management is a lot about extrapolating and forecasting. And so these are the three applications. Like learning about unknown parameters of the population. Second is testing theories, and something that, for example, we're going to do with the capital asset pricing model that shows some evidence whether it holds or not. And finally, forecasting. So that means that for every risk measure, we have one formula from probability theory using expectations, and we have one to learn about it from historical data. Now, and there are also different ways of how we're basically working with this. So usually the examples on the left, we're going to solve using pen and paper, like problem sets, right? And this could be exam questions as well. I mean, risk measures are the foundation of finance, so it's not a secret if I tell you that you might have to compute a risk measure in the exam, right? It's one of the core things, and we come back to this quite often. Now, how do you work with data? Well, with pen and paper, it usually doesn't work. So I have a case study for you that I would like to do with you, and we will, of course, solve that in Excel. So I was wondering a little bit of how we could time this in terms of our semester, because we have those 2 weeks where we meet online, right, and the week before and after Christmas. And I think that maybe the Excel part would be very much suitable for the online sessions, because I'm not quite sure. I see some computers here, but not everyone has the computer with them today or in class. So, and that would be very easy because I can share my screen online. You do sit in front of your computer anyways when you do this, and we can do the case study together. Right? So, I think it might make sense to do the data work and this perspective then in those 2 weeks. And today we're going to start with the left part. Introducing the risk measures in that forward-looking perspective. Good. So that sets the stage a little bit. Maybe before we, just another kind of upfront comment before we jump into this. We've already talked about what a return is, right? And I just want to remind you of why are we actually looking at the returns and not prices themselves. And risk measures are basically using returns as the data, not the prices, like share prices. And there were several reasons for that. So one comes basically from the world of statistics, that prices usually have trends in them, so they're upwards, usually trending upwards. And the problem is that if you now measure some key statistical numbers like a standard deviation, they will be different depending on the price level. I think I just looked up the share price of a company called Berkshire Hathaway yesterday. The share price is 430,000 euros, right? So it's a pretty large number. It's the most expensive share in the world. So that will have a fundamentally different standard deviation like a share compared to a share which trades at 10 euros, right? Standard deviations of prices are expressed in euros or dollars. So it's very difficult to work with data and statistics that has trends in it. So we call these time series non-stationary. We do prefer stationary data. And the properties of returns are remarkably stable over time. Right? So if you just take the percentage changes of the prices, it's much easier to work with in statistics. Right? So that's why we do use returns. The second argument is from the theory area, because usually we want to, this involves probabilities and distributions. So again, if you define probabilities, probability distributions for prices, you might run into a problem. Say you use something like the standard normal distribution, right? You've seen the bell curve before, right? The problem with the bell curve is that it basically never stops at the left and the right-hand tail. So there will be a positive probability for negative results, right? And if that's a share price, it doesn't make sense. Share prices should not be negative, right? So this area that you have here, that's the 0, is giving you a little bit of a headache for theories. Even if the probability is tiny, it's something that, as a researcher, you would like to avoid.